Yes, Roger. Good evening, members. You're welcome to today's ProDev Hour. I would like to welcome Mr. Bernard to give us an opening prayer. Mr. Bernard, give us an opening prayer. Mr. Win Samuel Bradley, if you can hear me, please give us an opening prayer. I think Bernard is still preparing to come back. Samuel Bradley. Can members hear me?
Yes, let us pray.
Yes.
Almighty, we want to thank you for this. Even we want to thank you for everyone who has connected. We want to thank you for keeping us alive, and we pray that you come and be with us during this session. Open our minds so that we can be able to learn something new. We pray for our speaker who is going to be sharing with us. We pray for all members who are not yet on, that you can be able to remind them they connect and be with us in this session. We pray all this in Jesus Christ our Lord.
Amen. Thank you very much, Rogers. Thank you very much, all who have joined in this prayer and those who are yet to join. I welcome you to today's ProDev Hour. We are seriously looking at how best we can present on the competency-based curriculum. We have looked at various components of the competency-based curriculum, and we realized that for us to implement the curriculum well or effectively, we need to look at all aspects, especially when we narrow this down to the science subjects. And the pedagogy of the curriculum in general is practical in nature. We talk about project work in all the subjects, irrespective of whether it is science or it is humanities. But most especially the science subjects, you can't do minus practical work. And therefore, today, in these professional development hours, we are privileged to have NCDC specialists, who is none other than Mr. Bonaventure, who is coming to share with us. He's a specialist of physics, and we always trust in what he does. Very competent, and is always on time. I would like to warmly welcome him to present what he has for us in today's ProDev Hour. Sir, you're welcome.
Thank you very much, Betty. I hope that is Betty talking. Who has been talking? Sorry.
Yes, please.
Yes. I hope you can hear me loud and clear.
You are very loud and clear.
I wanted to request your ICT side to enable me to share the screen so that we proceed. And I once again want to welcome you to this sharing. I wouldn't want to tell you that you have come to so that I feed you with everything, but this is really sharing. We keep on learning from one another as we push our science agenda forward. I want to welcome all of the participants. My name is Yaruhanga Bonaventure, as you have heard, curriculum specialist for physics. And in this 1 hour also, we shall be sharing about the practical investigations in science. And you will keep on noting some areas of interest so that we see how we can push this agenda forward, like I had said before. Trying to magnify, I don't know why it is not accepting. Rogers, please. Rogers, I wanted you to help so that. Are you getting me right, by the way?
Yes. Media co-host down there. There is where there is
Okay.
share down.
Okay. Yes.
Yeah.
I'm there. It's okay.
Yes.
Thank you very much. So, as we begin, we wanted to ask ourselves, what is the aim of teaching science subjects? That's one thing we need to reflect about. The second one is, how do we teach science subjects? The third one is, what is a scientific investigation? So as we go through this presentation, through this sharing, we shall try to reflect on those three questions. There could be others, but in the interest of time, that's what we need to look at. What is the aim of teaching science subjects? How do we teach science subjects? What is a scientific investigation? To begin with, there are so many other reasons that we advance here and there. You know, we teach so that we become doctors, we become engineers, we become this and that. We pass these subjects. But is that the end? Probably yes, probably no. Most likely no. How do we teach? Yes, I know that we are discussing, many of you are gurus in the subjects you teach, biology, chemistry, name it. How do we teach? Are we the type that is going to class from the beginning of the year up to the end, and we are feeding learners with information? Then, if that's the case, if that's not the case, what is the best way? And that one leads us to the third question: what is a scientific investigation? Before I proceed, maybe I wanted to remind ourselves about one of the scientists. It's not in my slides, but is said that education is not about teaching the mind. Those of you who have internet, you will check Albert Einstein when he lived. Hello, I'm being notified by that my internet is not very stable. I don't know whether you are still following me.
Yes, we are following.
Okay, thank you very much. So Albert Einstein is one of the people who lived, who was a scientist many years ago. Those of us who have internet, yes, we shall get internet and you check when he lived. But he had already mentioned that education is not about filling the mind with facts. It's about teaching the mind how to think. Incidentally, for us in the modern day, we think that learning is about filling the mind with the facts so that the learner gets out when they know everything, when they are like an encyclopedia. So we need, as science educators, to shift from that thinking to the approach that was proposed and that has been talked about by many other theories of education, especially the constructivists. The constructivists who talk about learners participating in the construction of knowledge, not being passive recipients of knowledge. So, having that in mind, it takes me to the second aspect, which is the meaning of practical investigations. What are they? Hands-on activities, but which are aimed to enhance learning in the science field. Hands-on activities. Ladies and gentlemen, in some cases, some of us, when we want to do what we are calling the practical, we do it for the learners. The learners stand there and we do it and we tell them that, haven't you seen? You are supposed to see this. You are supposed to observe this, even when they have not observed it. And that is not good. It's not a scientific investigation. It must be hands-on. learners must fold their sleeves, must make their hands dirty, and do the activities in the process of the learning. This fosters inquiry. Learners begin asking why they are seeing what they are seeing. Then they begin thinking about it. And then the next thing is, can we solve issues relating to them? It's not about us, the teachers, going and telling them that it is supposed to be this, even when it has not become like that. There is a time there came to the teachers on the forum, please, who are online, please, I'm using this one as an example. A teacher went and did not test the solution and was teaching about litmus and the color changes of those acids and whatever, as you know, those of you remember that thing. And threw some blue litmus in a substance which he knew was an acid and knew it was supposed to turn red. And when he threw some blue litmus paper, there was no turning red. But the teacher was saying that it is supposed to turn red. And the learners were saying it has not turned red. And the teacher was saying it is supposed to turn red. So what does that mean? There is now inquiry. It is not about what is supposed to be. It is about what it is. Critical thinking. Then we need to begin asking ourselves, why hasn't the litmus turned red? For you, the teacher, for me, I said it is supposed to turn. So we are now going into critical thinking, and that is what is at the heart of an investigation. So learners, in this case, engage in scientific processes. They are not only passive recipients of information. They are not only told that blue litmus is supposed to turn red when it is dropped in an acid. They are supposed to do it. They are supposed to prepare for it. They are supposed to plan for it, as we shall keep on seeing in this presentation. They are supposed to observe. And what about if the observation is not what has been predicted? We shall be talking about that. They are supposed to now analyze the observation, or do data analysis. Then they are supposed to compare the observation or the results with the prediction. I will be talking about that one slightly later. In this way, the gap is narrowed or bridged. Ladies and gentlemen, those of us who are listening, we know that we talk about this so many things. Why this is like this, this is like this, this is like this, and we stop there. That is in the classroom setup. But when we go to the real world, we need to connect the classroom with the real world. Because what we learn is not for the classroom. We learn so that it becomes a product for the world. And that one is going to be achieved if we can teach and learn through scientific investigations. That makes us and our learners not passive. So, what then do we aim at if we are supposed to do a scientific investigation? If learners are supposed to go through scientific investigations, there must be inquiry. Learners develop inquiry skills. We shall talk about that one as we move on. Learners move beyond theory. They develop skills in designing their own experiments. Ladies and gentlemen, in the older systems, we were used to only learners doing experiments by following a set of procedures which are predetermined. Yes, that is one way of doing the investigation. But if we are to do the investigation and become more scientific, we have to mix that one with another format. And that format is where learners develop the procedure themselves, basing on a hypothesis. I will talk about a hypothesis in a little while. Learners become active. Learners become active and they play an active role because they do hands-on tasks and research. They are not passive recipients of knowledge. So they are not going to sit down and be told that blue litmus stand is red. They are not going to sit down and wait that these are the factors or these are the conditions that affect the germination. They are not going to sit down and wait and be told that, light can be split into different colors. They are not going to be told that, when you look at this material, its refractive index is this. No, they are going to actively participate in trying to get it themselves. And they will develop essential skills. What are these skills? One of the skills that will be developed is observing. What then is observing? Observing is that skill of using the senses to detect changes, using our senses. Yeah, whereas depending on the nature of the investigation, we limit some of the senses from being used, but we use our eyes, we use our feeling, we use our ears, we use our nose to smell. Yes, we may use our tongue, but we may limit that onto a few experiments or investigations, but using our senses to detect changes and make observations and record what we have sensed by our senses, what we have detected by our senses, is an essential skill in a practical investigation. What have you heard? Is it a sound? It may be a sound. It may be a color. It may be a taste. It may be a feeling. It may be an appearance. You can name it. Looking at details. That's observing. Then we also have to develop among the learners the skills of measuring. Measuring. Taking readings. What then is measuring, ladies and gentlemen? That's where we use an instrument and we determine the worth of a quantity. So then we also analyze the observation, data handling, and analysis. There is also developing our motor skills. Our hands are able to handle apparatus, maybe with care. Some of the apparatus could be heavy. All that one is very important. How do we handle apparatus? That is in practical investigation. Safety skills. Learners are supposed to practice safety. If we are dealing with whichever type of investigation, how do you take care of yourself and your neighbors so that you get out when you are safe and you have observed? Is the investigation going to put you in trouble? One time, one of my colleagues gave me a story that he went to the UK and was doing team teaching with teachers from the UK, and gave learners, younger learners, I think the equivalent of like senior 2 in our case in UK, to get a razor blade and cut some object. I don't know whether it was biology or I think it was mathematics, cutting some shapes, maybe circle or something like that. And then the learners refused. And then the African teacher was saying, why are you not doing the investigation? We want to make these shapes. The learners were saying, no, but now if we are telling us to hold the razor blade, you are not telling us how to hold it. What if the razor blade cuts my body? What will happen? How will you take care of me? You have not told me how to use the razor blade safely so that I use it during this investigation. So this is what I'm talking about, safety skills. We just say, okay, go and hold the glass blocks, go and hold this, go and use the compasses and so forth for doing these constructions in mathematics, in physics, we are using lancets in biology, we are using acids in chemistry, we are using alkalis, we are using what in agriculture, we are using pangas and so forth. Are we talking about, are we emphasizing the issue of safety? This is where learners are supposed to be cautious and conscious about what they do. And that is very key in as far as scientific investigation is concerned. So, ladies and gentlemen, when we teach learners science without having them go through scientific investigations, we rob them of some of the things we have mentioned here. Inquiry methods, learners don't develop skills of designing experiment more on the hypothesis. Learners do not have an opportunity to play an active role in doing hands-on activities and even research, comparing what they see with what is in theory. Learners don't develop those skills that are not only pertinent in practical investigations, but are also essential in life. Yes, we are handling apparatus, but we shall handle so many other things in our lives. We shall handle so many equipments. We are talking about safety. I don't have to emphasize that. We are handling data, yes, and analyzing it. Learners will meet different sets of data and information in their lives, and how do they treat it? So we need to see that this is very, very essential in as far as teaching and learning of science is concerned. Investigations or practical work may take the form of being descriptive, where learners only observe and make observations and discuss them and compare them with what is in theory. Like I had said previously, we want to bridge the gap between theory and real life and the real world. What can be about comparing items or testing some variables, for example, where we do experiments. There are so many other things. We are talking about acceleration due to gravity of around these places, this and that, the pH of what is this and that. These are the factors that are affecting germination or whatever it is. But do we have a way we can help our learners really reach out to that in an experimental way, or we talk about it? The aim here, members, is to make sure that we don't teach learners about science, but we need to teach learners science or scientific methods. It is a problem that at times we teach learners about science and we think we are teaching science. And when our learners participate and they pass in these examinations, national examinations, we are very happy somebody has scored an A, but actually there is no science in them. They learned about the science, they didn't do the science. And the new curriculum and this sharing is there to reinforce us to change. Now, practical activities or practical investigations can take various forms. One of the forms is open-ended activities. You don't have predetermined outcome. You don't know what's going to come out. You don't know the end. We want to allow students to explore examples where an investigation is carried out. Oh, sorry, internet instability. Please, you tell me when internet is not good. Where activities are carried out, and then there is a discovery. We don't tell learners what they are going to do. Learners go through certain procedures which they themselves can formulate, or which are with the help of the teacher, without knowing what is going to be the outcome. They do this, they do that, then they come up with something, and what they have come up with something That's when we can conclude that, okay, actually what you have come up with is this. And that is a discovery. That is exploration. There is a misconception that learners in senior 1 or in senior 3 cannot do an exploration. As long as we can not have these experiments, if I were to use my physics, my physics experience, sorry, not my physics, but the physics experience. In this experiment, you are going to determine the acceleration due to gravity using a spring. Then, in that case, you have not given an open-ended task. The learners are not going to do an open-ended task. They are not discovering anything. But if learners can go through procedures, through steps, and then they come up with something, and then we can conclude and say, hey, what you have come up with is that A, it has become 1. Yes, now that's the density of water. What have we discovered? Put some seeds in here. Do this. What have we discovered? Oh, there is moisture there. Then why is the moisture coming? Where did the water come from? I think there was a process in the seeds that led to giving out the moisture. And that one is exploration. So that is one way of doing the practical activities. The end is not predetermined. The second one is where we have an extended activity which takes slightly longer period, more than with some weeks, maybe, if I were to put it that way. And the commonest is now what we are talking about, project-based learning and projects. That is, I think, in that line. Not only 1-2 hours. There is this tendency. At one time, I was interacting with the university students, and they went to do some experiment, and they came out to the results expected. These days we also know what we expected. They went and the results were not what they were saying. And I was telling this with the results, without results, or with 1 or 2 things. Then you have to go and repeat. Then you have to go and repeat. That is now what is called scientific inquiry. Then you have to go and change the method. Then the result is not obvious. Then you may not get what you expect. Then you begin inquiring, asking yourself, why has it happened this way? What does this one mean? What does this observation mean? If I were to use to draw the experience of the other teacher, of the blue litmus, you have put the litmus in a substance. You expected the blue litmus to turn red. It has not turned red. Then the question begins to come. Why has blue litmus not turned red? Then the next thing is to test that solution and see whether it is actually what we expected using known procedures. The chemistry people know that. The next thing is, if we can use this litmus in another solution, will it turn so that we rule out the possibility of this litmus being the problem being something else? That is now the inquiry. And we can do that one over a long period of time. Sometimes we need to encourage our learners that they will not get the reading, the expected observation. Obviously, it may not be, and that is not a problem. This is the other thing of saying that, okay, I have been determining the refractive index of this material, and we know glass is 1.5. What if you are provided with a substance which is not glass, and somebody has not told you? Somebody has not told you that the material you are dealing with is glass. You are determining something there, and you come up with 1.2, and you say, this one cannot be refractive index. So this is the thing that we want to develop among our learners. Activities which are done over and over, where even the observation is not obvious, where conditions change. If you are dealing with biology, maybe agriculture, you are dealing with germination. I don't think that you will observe germination, processes and conditions and all that in 1 or 2 lessons. It must take a long period of time. You know that the normal seed is maybe 4 to 5 days, or if they are to go to a certain height and certain leaves. So the third one is structural investigation. This one follows procedures which are answering a specific question. I think this is the traditional one that we are using the two, and it is one of them. Yes, we are not saying it is completely wrong. You have those activities in the learners' books. I think all of us who are teaching at least lower secondary, we have that. We have those activities. Activity 1, do this, do this, do this. What do you observe? What do you mention about this? What do you conclude? Those are examples of structured investigations. Yes, the activities that we have in our books, learners' books, are rich in that. So we shouldn't misuse those activities by telling answers, predetermined answers. Still let learners carry out these activities and they reach up to the end. Now, if we were to carry out an investigation and that investigation is not structured one, is in the other two categories that I have mentioned, open-ended and extended, what then would be the steps that learners, participants will go through? The first one is making a hypothesis. What then is a hypothesis? A hypothesis is a prediction of the outcome. If you are given a stone, then, and we tell you make a prediction about it, people can make different predictions. Somebody can say, I think this is gold. Somebody can say, it's dense, it is heavy, its density is about this. Somebody can say this and that. It can be used for making cement, and so forth and so forth. So that prediction is called a hypothesis. It is based scientifically on the I see, I think, I wonder. Those three short phrases. I see, what you see, all of us see things. The next thing is I think. Okay, I think it is this. That's a prediction. I wonder what it is made of. That's then you are going to carry out an investigation. So I think is a hypothesis. Then I wonder is now the problem. So making a hypothesis is very, very important. Making of what you're supposed to do, it is what you get. This is only what directs you. And that one takes you for further inquiry. It takes you for further investigation. If you think that something is gold, then what are you going to do to test your hypothesis? Because the remaining stages are testing your hypothesis. You are going to measure some known properties of gold. It may be density, maybe. It may be conductivity, if it is there, I don't know. It may be refracting properties. It may be heat conductivity and something like that. You have got an unknown liquid. Oh, there's a liquid there, like I have here in my bottle here. I have this liquid. But even if I'm very thirsty, unless I'm assured that it is water, I can't take it. So before I take this water, I will have to first water. Why? Because it's the known properties that will confirm that the liquid is actually water. But in a hypothesis, we don't make conclusions basing on hypotheses. So hypotheses are imaginations, predictions, which our learners need to learn to practice. Then we have to plan the investigation. If I think that this liquid is water, what next do I do? I need to carry out those investigations that will lead me to the conclusion that actually it is water. And this one is not done once. Even if I come up with the conclusion that it seems to be water, I need to repeat this a number of times. Learners need to repeat the investigation number of times to see that the conclusion is valid. We talk about validity and reliability. The concept of reproducibility is very, very important. Single readings do not form a conclusion. Then, after planning, then you plan the investigation, looking for which steps you are going to go through, designing procedures, selecting and sorting required apparatuses. What will I need? Will I need a barrels? Will they need litmus? Will they need thermometers? Whichever investigation you're talking about. You can think about the investigations from your subject point of view. Then recordings and readings or observations. Ladies and gentlemen, there is the concept of reproducibility under the same conditions. Taking readings, a single reading, measuring the mass of something, and it becomes what it has become, and we do it once, does not inform good scientific methods. We are supposed to try out the same experiment a number of times, remembering that some of these investigations are not only for single lessons, some of them are taking long. So we need to encourage our learners to repeat and see whether the readings are consistent. If readings are not becoming consistent, then our conclusions may be unreliable. The observations, learners should analyze their observations vis-a-vis their hypothesis and then make inferences. Ladies and gentlemen, analyzing observations depends on the observations that are made actually. Are they qualitative? Are they quantitative? If they are quantitative in terms of figures, then they are patterns that are based on to make conclusions. Identifying the patterns, identifying the lowest and highest values and such behavior. Then, of course, the observations are tested against the hypothesis. If you say that this is water and what you have come up is this, can you conclude that your hypothesis was correct, or can you now go into another direction to make another conclusion? I want to repeat this. Hypotheses are not conclusions, are not inferences. Inferences are made after thorough experimental procedures. So let us encourage our learners to appreciate that. When I say that this stone is gold, that's a hypothesis. It's not a conclusion. It is the experimental steps that will help me to conclude and say that this is gold or it's not gold. So these steps, yes, there could be minor steps, but in the interest of our discussion for today, these are the major steps that learners need to practice, need to go through when they are carrying out investigations. So, why should practical investigations be part and parcel of the teaching and learning of sciences? What is the benefit? Definitely, the first one is that you have engagement, hands-on activities that stimulate curiosity and enthusiasm for science. We need to move away from teaching about science, but teaching science as much as we can. I want to really appreciate that we are not properly resourced in our environments, in our different schools, but where it is possible that some of the experiments can be done, let us not short-circuit our learners. Let us not rob them of the chances of gaining the curiosity in doing some of the hands-on activities that are possible. Even to the smallest city school in the country, there are certain activities, investigations that are possible. Some of the schools are resourced naturally. We have some of the investigations which will depend on natural environments, the plants, the crops, the soils, the rocks. Let us try to do them. Those of us who have got industrial apparatuses and so forth. Let us try to see, so that we help our learners to have hands-on activities so that they become curious and enthusiastic. You know, there is that always longing. When I was in senior 2, senior 3, the lab lesson would be the one where you would feel really going to the lab, you would not want to miss. But those of you, the teachers who are teachers of ICT, you know how learners go to queue in front of the computer lab. Those of you have it before the computer lesson. That's the enthusiasm we are talking about. But if all the science lessons are done in the class, boring, talking about some things, writing about complicated equations, writing about big diagrams and so forth, then our investigations, our engagement of learners will be hampered, and then they will not have that enthusiasm for science. But if they are willing, if we take them to those environments that will help them to do some discoveries, minor though they may be, it definitely will be very interesting. And again, it improves the understanding of concepts. Theoretical concepts are enhanced, reinforced by practical experiences, and this one encourages mastery. That acid, which you say is that an acid, for the simplest way to test that a solution is acidic is to see that it turns blue mass to red. That one alone helps learners to understand the concept of acidity. So we talk, teachers, we have so many concepts that learners that remain hanging, but does it exist sincerely? You know, wheel and axle, you know, pulley, you can name it. In biology, and you are talking about, you know, the blood is flowing, and some of the investigations can be done using simulations. I think I have to say that, so that the learners have some hands-on experience. Yes, some of them are not as easy. I have never seen electrons. Most likely I may not see them, but some simulations can still be bring out the activities. So there are these things that the learners keep on wondering. A magnet attracting another, but does it happen really? But what about if we can see it? You know. So we talk about this, we talk about that, and then learners are still. But do leaves give out moisture? How? Do seeds give out moisture when they are germinating? So these things theoretically are there. We talk about them. Those concepts are very many, but without practical experience, learners will keep on wondering. And therefore, this improves the mastery of concepts. Then there is also the real world context. We are trying to connect the classroom to the real world. And in this case, that we are talking about practical investigations, which are scenario-based. Ladies and gentlemen, we need to remember that these learners that we teach are not going to be in class forever. They will leave the classroom and go to the real world. The world will not demand them to only speak about the concepts, but the world will demand them apply the concepts in solving real world challenges. So we need to prepare them for the practice of problem solving. And problem solving is achieved by doing, not by talking about. Then there is motivation for innovation and invention. Innovation and invention. Sometimes we mix the two, but innovation is all about modifying, making something better. Invention is about coming with something completely new. This one cannot be achieved without hands-on experiences. It cannot be achieved by only talking about this, by talking about things. It will only be achieved when we make our hands dirty and we try to do something. So learners need to grow as they go through this education journey, knowing that they thinking beyond what they see can bring out something new and can bring out something that helps in solving problems that exist in our society. And that is only achieved if they can have hands-on experiences, hands-on activities, that mind of imagination, that mind of hypothesizing. If I do this, can't I get something like this? Now that is innovation. If we combine this and this and this, can't we get something like this? What does it require for somebody to get something like this? And that one is only achievable through hands-on experiences. Now, once again, I would want to say that we don't have to rob our learners of practical investigations, especially in the science field, because we shall be robbing learners of some of these benefits and many more others. Think about yourself, ladies and gentlemen, when you did an experiment and you got an observation which is exciting. What came to your mind? Those of you who studied from small schools like me, if you did something and you would see something exciting, hands-on. The teacher is very essential and has roles to play in the science investigation. We are developing a science mind, yes, but as teachers, we are not going to fold our sleeves and sit down and go to TikTok and say, okay, learners are carrying out an investigation. Our supportive role is not going to be diminished. It is supposed to remain. So what then is the role of the teacher as I try to wind up this sharing? The role of the teacher can be divided into three. There is the pre-investigation role, the during investigation role, and the post-investigation role. Remember that these investigations are not only being carried out for the purpose of examination, they are carried out for learning. So before the investigation, what is the teacher supposed to be? He's supposed to play he or she is supposed to play the role of the planner and facilitator. What does the teacher do therefore? Yeah, there is safety assessment, both for the apparatus, for the environment, and for the procedures. If this is a procedural experiment where the procedures have been set and given, the teacher is supposed to test and see that the apparatus to be used is safe or provide safety guidelines. The procedures to be carried out are safe or provide safety guidelines. The environment is safe. If learners are going to carry out an investigation of looking at how birds or animals are behaving in the open field, what safety are we talking about? How should learners behave? Or the teacher just says, you go to the bush. No, there is that safety assessment, and then there is also the preparation to put in place the required materials. You are going to catch insects for this and that. Do you have the quadrants? Do you have the nets? Are they available? What about the groups? Will each learner have one? So it's not an issue of the teacher going just, on Tuesday, there is going to be an investigation experiment by learners. Okay. Then on Tuesday is my holiday. No. Teachers, please, that's not your holiday. You are not going to sit on TikTok. You have roles. Then the teacher helps, shapes, in setting up the driving question. If it is an inquiry question, how can you show that an unknown material is gold? How can you test that this is gold? That is a driving question. How can we test that germination requires this and this and this? How can we show this? So the teacher frames the driving question and defines the scope of the investigation, defines the extent of the investigation. If it is an investigation within a lesson, the teacher's role is there at that time. Now, during the investigation, the teacher now becomes, the other one has been, before the investigation, the teacher has been a planner and a facilitator. During the investigation, the teacher is now becoming a guide and a monitor. Once again, whether it is an investigation within the laboratory or within the school compound or outside the school, the teacher is not going to sit with the folded and crossed legs, folded hands and crossed legs. No, the teacher is going to supervise whether learners are ensuring safety, remembering that teachers, if a learner gets hurt during the investigation, then we can be charged with professional negligence. And remember, investigation is learning. It's a process of learning. It is not fun only, but it is learning with fun, or fun with learning. I don't know which comes first, but there is facilitating learning. So we are supposed to assist the learners. The teacher is supposed to be assisting learners in taking readings, in taking observations, in correcting the specimens, in dealing with the specimens, and such things. And then the teacher keeps on also making probing questions, keeping asking, why are you doing this? If the investigation is open-ended, then there is the teacher ensuring that the inquiry, the investigation follows the time scheduled for it. We need to note that investigations will not last forever, given the limit of the school calendar. Yes, if learners get out and they will be working in environments such as the Industrial Research Institute and others, which are basically for research, then that is a different environment. But at the school setting, because you know that, for example, those researchers who come up with new crops or new varieties, I don't take maybe years, but in a school setting setup, it may not be like that. They must achieve these ones on schedule. So the teacher is supposed to ensure that. And what about when the investigation has ended? The teacher's role changes to the evaluator. So the teacher is a planner, the teacher is a guide in the investigation, the teacher is an evaluator. Remembering that investigations, once again, are a part of the teaching and learning process. They are not only for the examination. So we need to desist from this habit of saying that learners do practicals, the first practical at mock or after mock, when you have predicted what will be in the exam. They will pass, but they will not be scientific. When they go into systems which want serious science inquiry, science investigations, they will have problems. And therefore, at the end of the investigation, even during the investigation, there is assessment and guidance. But then at the end of the investigation, then the reports are given to the learners. The skills of assessment, especially data analysis. Handling apparatus can be done during and at the end, but especially during. Maybe here there's need for some adjustment. But analyzing results, what did you observe? How do you compare this one with our hypothesis? What does the reading imply? What does it mean? That is the assessment. Then there is consolidating understanding. That is reviewing the results vis-a-vis the hypothesis. If the hypothesis was this and the results are saying this, what is it? What does it mean? Then that is the teacher's role, so that the learners make inferences basing on the hypothesis. Basing on the results. Then feedback is given to the learners, and then the learners can interpret basing on their data interpretation, and then they say they have been successful. We want to also remind ourselves that even if an investigation has not been successful in terms of the hypothesis, I mean, if I tell you that go and dig the other place and get gold out of it, or test this soil to see that it is gold, and you say that it is not gold, but basing on certain observations, then that still is an investigation and it is successful. So success in an investigation does not necessarily mean that you get the expected, but you may not get the expected going through the best necessary procedures. And that is more important. That is what we encourage. So feedback must be given to learners in terms of safety, in terms of preparedness, in terms of handling apparatus. Apparatuses will be different, and that is what will constitute a science practical investigation. Ladies and gentlemen, thank you very much for your kind attention. I will beg to stop.
Oh, thank you very much, Mr. Bonaventure, for this elaborate details into practical investigation as we teach. I am very sure members here have enjoyed the sharing. I would like to, at this time now, open up a discussion. If any member would love to ask a question or add more to what you have said, a member is welcome. Please, you can raise up your hand and have a word or two. Welcome.
Questions, please.
A good science teacher or a good teacher in general is a teacher who is able to practically teach in class, who is having lessons hands-on. They help the learners to touch, they help the learners to use all the five senses actually, to discover, to explore, and they're able to explain and analyze situations. And this is when they're able to practically apply what they have learned in class, because I believe that practical teaching or investigation helps a learner to get a given concept to exactly what it means in the community or in the environment. So practical teaching should be part of a science teacher, especially as we teach. I don't know if my feelings is the same as for others who are here on this ProDev today. Has what been spoken here been different from what we have in class? Have you gained something that is going to make you a bit different in the class? Can we have a small sharing? You're welcome.
Members, please, some sharing, some inquiries, some comments.
This is an indication that the sharing has been very elaborate. Members have understood what it is, or it has reminded them of exactly what they should be doing in class. It's not a very big deal to ask any question.
I don't know. So members, wherever you are, please raise up and we share.
I can see Jacob already on and is ready to talk.
Okay.
Thank you very much for guiding us on the pedagogy and science. I'm just giving an application for the year the science discourse. Yes.
Jacob, you're a bit far from the microphone, from the phone.
Yeah, I don't get Jacob clear, sincerely.
I'm very far. Can you hear me?
Yeah, slightly better.
I'm just making an application for your work. Thank you for directing us on the pedagogy, the science. You see, actually, the teaching of science is one with the current curriculum, whereby we abandon that structured investigation which was used to the old curriculum, and we make students participate in the the investigation. They own the investigation. Thank you for enlightening us on that. That's what I wanted to add. Most schools, people who are still on the old way of carrying out science experiments, but we need to adopt the new curriculum approach, whereby the learners derive their own procedures of science investigation, so that they own what they have learned. That's what I wanted to emphasize.
Okay, thank you very much. Okay, thank you very much. I heard your name is Jacob. Yes, mindset change does not happen in a day or two. It is a journey. I know that we may be misunderstood, that passing is not necessarily good learning. There may be somebody who may get the very good score or the A in the science, but having been coached, that one does not necessarily mean that they have learned. The world will keep on judging us for doing something that is wrong, although we glorify it. So we keep on encouraging our teachers to let the learners do the hands-on activities in the small, within the limited resources that there may be in the environment. Still, yes, time limits are there, but let learners do some investigations, whichever way, because otherwise we shall rob them of what we talked about, those very many skills, including communicating ideas and reporting results, because the world will demand them from them when they have left our care, when they have left school.
Thank you. I see Mr. Echakara James ready to talk. Yeah. James, you're welcome.
He's very welcome.
We're having the last person today, Mr. Echakara James. I can see you ready to talk, please. Welcome. If James is not ready, Rogers, do you have something to say?
Yeah, I just wanted to inquire. In the old curriculum, I personally remember from my A level, yes, we used to enjoy the practicals like physics, and we have our teacher had some serious physics practicals. Even there's a booklet, and we go there, we put those masses, the pendulum bobs, and all those things, and we draw the graphs and all that.
Yes.
What I was inquiring is in the new curriculum, because there is a procedure, you just have to follow. I do this, I plot the graph, and that's all.
Yes,
is there any, when it comes to practical activities like in physics, in the new curriculum, are they still there, or there is, what are the dynamics when it comes to that?
Thank you very much. You and I studied from that system where we would be given procedures, and we just go through procedures, whether we understand what they mean or not. And then we were told that, in this experiment, we are going to determine the acceleration due to gravity using this method. Then in the next way, we are going to determine the mass of the meter rule. But somewhere at the end of the day, even you would not be told that you are going to calculate the mass of the meter rule. You would be told to substitute in a formula, and what you get, you don't know that is the mass of a meter rule or not, but you have gone through all of that rigor. And then later we say, in this experiment, you are going to determine a constant x for a mass, for a meter rule. But then we are told that calculate the constant x, and then we stop there. So what does that mean? It means that the investigation has been basically following procedures and writing observations. And that is not a complete investigation. The learners have not made a hypothesis. The learners have not related the results to the hypothesis. Yes, they have done some middle things, procedure, observations, data analysis, but they have not compared. They have not considered health awareness and safety. They have not considered issues to deal with stability and the errors. So the dynamics that you are asking about are there. that yes, that this one of following procedures, blah, 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 is one of them. And I think I elaborated in my types, but it is one of them. But we are adding there another ingredient of where learners make their own procedures, select their own apparatus, and make their hypothesis. Hypothesis is very, very important. In the old system which you are talking about, which you and I went through, we never made a hypothesis. We would just say, nobody was asking you what is the approximate mass of a meter rule. At least you say that it is 60 grams. And then you test whether it is going to be 60 or not. But this time we are also adding the ingredient of a hypothesis. Yes, there are some few, the dynamics are there. Learners plan their own investigations. They make their own procedures. They do the data analysis. They consider issues of errors. Thank you.
Thank you very much. Madam Auma, I think you are there.
Yeah, I'm there.
I just want maybe to just say something small. Mr. Bonaventure, thank you very much for the presentation.
Welcome, sir.
Yeah. So there is someone in the chat who was asking about his internet was not okay. So I just want to, that was Lucy Tumubuene. Yeah, we are going to have this session recording. We are going to prepare it very well, and we are going to publish.
Lucy Tumubuene is from which side? I think that one even could be my classmate.
Okay.
It's a college long ago.
Yeah.
Yeah. That's great.
So, yeah, this ProDev really has a lot of rich lessons, and many of these I know are shared in various trainings NCDC normally does, and many other. But sometimes some of the members, this is now an opportunity for us to keep learning. So
Rogers, I will send you, and Betty, I will send you the slides.
Yes, thank you very much. We shall be grateful to share it to members.
Okay. So we are going to have it available. Also, we are going to have a post on the website, and we shall be sharing on the platforms. Yeah. Thank you very much. That's all I had. Over to you, Madam Betty.
Oh, thank you very much, Mr. Bonaventure, for helping us this evening realize that without practical activities, our lessons for sciences will not be bringing the real meaning. I do not know if you have, maybe you could conclude for today's presentation before I ask someone to conclude it. You're welcome, sir.
Okay, thank you very much, Betty. Thank you, Rogers, and thank you all the members for the participation, for the presence. We are always very, very happy to keep sharing these ideas. You know, changing a nation is not an easy job. Changing a perception that we have been having requires all of us to do our bit. So we thank the organizers of ProDev for always giving us this hour to share with you, to learn with you. It is a journey that we started to improve our education system in the country. We shall always keep on sharing. Whenever given an opportunity, it is not a one-day's event. We really thank you very much for the initiative. And I want probably to say that science teachers, you are beginning to really impact. You are beginning to impact, and keep on moving on. You will really achieve. It was, I think, a movement that started by one or two, and try to reach out to almost all of the members, all of your members in the country, so that you move together and we improve the learning of our learners. Learners, wherever they are, whether you are posted in a very small school like the ones which we attended, city school, please Let us do our very best to let learners do some hands-on activities so that they can discover, they can explain some things, they can apply, they can analyze, and you will not regret. I want to once again want to thank you very much and have a good night. Back to you, Betty.
Thank you very much. Your moderator has been Betty Auma, National Coordinator for Education Professional Standards of Uganda Professional Science Teachers Union. I want to say I'm very grateful on behalf of the union to you, Mr. Bonaventure, who have represented NCDC. Thank you for always accepting our humble requests and coming to give knowledge to our teachers. We are promising that the memorandum we have signed has not ended, it will continue, and we still continue expecting more bigger topics that we are going to share here on this ProDev Hour. I say everybody, please may the Almighty God that has granted us this evening and has given us a special attention continue blessing us wherever we are as we depart back to our other activities. As I announce members who are on the Central Organizing Committee for Science Innovation Projects 2026, tomorrow we shall have an online meeting. Please stay tuned, you'll receive messages and the Zoom link we are going to use for this meeting. The meeting is going to take place at 4 p.m. in the evening as we had planned. I say all this for God and my country. Good night to everyone. Thank you.